Good morning. How are you, sir? Can you say something again, Mohammed? I think I had the wrong speakers on. Okay, perfect. I hear you perfectly. Thank you. Good morning. I'll give it 1 or 2 more minutes for more people to log on. Okay, I have 2 minutes past, so maybe we should go ahead and get started. So we have some business to discuss as far as updates on the homework and whatnot. So I spent Sunday doing the grading, and I believe I am all caught up now on everything that I have in hand. So I have all homework ones fully submitted and fully graded. So those have been graded and returned to you. Since everybody's submissions are in, I have made the solutions visible on Canvas. I will switch to share screen in a minute and walk you guys through that. Homework 2, I had 8 out of 14 on hand. So I'm still going to be flexible with submission deadlines, but you run the risk of sliding further and further behind as time goes on. So try to keep up with those as best as you can. I will grade them periodically and get them back to you as soon as I have them in hand. And once I have everybody's, or once it goes by too long, I can't afford to let it go on any further and I need to post the solutions, then I will cut off submissions and I will post the solutions, but we're not there yet. So there was a question raised about whether we would do homework corrections this semester. I hadn't made a firm decision one way or the other, but I'm open to doing so. It wasn't really a big deal last semester because we only had a few assignments. This semester, I think we're on track to do a lot better. So it's more grading. It might slow me down a little bit on this program, but I am willing to give you the chance to resubmit homeworks that you messed up on for the chance to recover up to 50% of the points that you lost if you will make corrections and explain your mistakes. If you're willing to keep putting in the effort and keep learning, I'm willing to keep putting in the effort and giving you points for it. Another thing that was brought to my attention is that there's some overlap between my scheduled office hours on Thursdays. I had done Thursday mornings since the homework is due nominally on Fridays. Apparently this overlaps just a little bit by about 30 minutes with StatMat. Let me know if that's a problem for you guys. There's nothing magical about this time slot. I just picked Thursday morning because it seemed to make sense since the homework is due the next day. But if this becomes a problem for you guys, let me know and we can find a better time. I think that's it as far as old business. Any questions or issues on old business? As far as new business, I posted homework number 3 on Canvas at the end of last week. That is due this Friday. This is the homework on addition of angular momentum. So same style as previous homeworks. There's one simple problem, which is a direct computation, and one more applications problem, which this one, I was very happy that I was able to adapt something from the 2019 comprehensive exam and sort of walk you through how one goes about solving it. So without further ado, let me share screen and show you what these new things look like. All right, is everybody seeing this? I've got Canvas up.
Yes.
Okay, great. So let's see. So here's the view of Canvas. I wanted to point out that as of right now in Student View Homework 1, solutions are visible to you, so you can go grab those. I've uploaded the various solutions for the other homework, but they're invisible right now until I have the submissions from everybody. So if you click on Homework 1 Solutions, this is what you will see. Overall, the performance on Homework 1 was very good. The first problem was simple calculations using the harmonic oscillator. People did a very good job with plugging in for the position and momentum operators in terms of the creation and annihilation operators. And that lets you directly evaluate these expectation values and show that the kinetic and potential energies are equal. People, again, generally did a good job of plugging in for the time dependence of a harmonic oscillator state. I think almost everybody got this part. And then if you carry it through, you get X, which behaves like cosine omega t, P, which behaves like sine omega t. There was a little bit of confusion, I think mostly just some minor calculus mistakes on part C here. A common issue was, let's see, so I think most people got this with the lowering operator. Common issue was forgetting that this derivative acts not just on the Hermite polynomial, but that the derivative also hits the exponential. That's important because you need that X plus P combination to cancel out so that only the derivative of the Hermite polynomial remains. So if you forgot chain rule, you would not have gotten this cancellation. The other thing that tended to throw people off a little bit was chain rule. When you take the derivative of the Hermite polynomial has this argument with a square root inside. And when you take that derivative, you end up pulling out an extra factor. The identity that you're trying to show at the end of the day involves a change of variables. So you might have ended up with an extra square root hanging around if you didn't carefully pay attention to the change of variables to absorb that square root. Let's see. So again, most people did pretty well on the substitution into the angular momentum basis. For this first problem, the exercise was to take cosine squared and decompose it in terms of e to the I phi and e to the minus I phi. That looked pretty good. People read off the probabilities. Just a general comment. I think a lot of people did a lot of extra work that wasn't really necessary to fix the overall normalization coefficient. Since you know the overall normalization coefficient has to be set so that the whole thing adds up to 1 at the end of the day, you don't really care what its actual magnitude is. All you really need to worry about are the relative coefficients. So if you end up with 1, 2, 1, this factor is whatever it's going to need to be to make it all add up to 1 at the end of the day. And you can just compare 1 squared over the sum of the squares of those relative coefficients. So people did a good job on this, maybe a little more work than was necessary, but that's okay. Problem 2b was very similar, except you were expanding in spherical harmonics. This looked maybe a little bit more complicated because your coefficients were complex, but as long as you remember to multiply by the complex conjugate, that it's not just squaring, but absolute value squaring, then it's really no more complicated than problem 2a. And I was very pleased with the performance in part C. As far as I was concerned, a simple statement or a claim that there's symmetry in the problem would have been enough to say that Lx squared and Ly squared are equal, because there's nothing in the problem that biases you to prefer X over Y. But many people actually did the algebra and proved that expectation value of Lx squared is equal to expectation value of Ly squared. So that was very good. And then the rest of that was some simple algebra. Okay, those are the homework 1 solutions. I also wanted to at least give you a quick preview of homework 3. So this is based on the material from last week on addition of angular momentum. The first problem is a direct calculation of the Clebsch-Gordon coefficients. So we in class had done 1 plus 1/2 and 1/2 plus 1/2. So this is the next simplest one where you are combining spin 1 and another spin 1. And you should show that this gets decomposed into 3 ladders: a j equals 2 ladder, a j equals 1 ladder, and a j equals 0 ladder, although that j equals 0 ladder is really just a single state. So you're calculating the Clebsch-Gordon coefficients. I kindly gave you the answer. This is the Clebsch-Gordon table taken directly from that table from the particle data group. So you can check your answers as you go if you remember how to read the table, which we discussed in class. So all of these parts are just about calculating the Clebsch-Gordon coefficients. I just assigned point values to each piece. 4 points for the main ladder, 3 points for the secondary ladder, 2 points for the leftover singlet state. And then 1 point in the beginning for counting the dimensionality to show that the number of dimensions you have in 1 times 1 is completely exhausted if you sum it up into 3 ladders of 2 plus 1 plus 0. So nothing special here, direct application of what we did in class. So this problem is one that I took directly from problem 1 on the comprehensive exam from last year. So this is a problem that you might not stare at it and go, oh, obviously I need to use addition of angular momenta, which is why it was good to break it down and walk it through step by step. So the first observation is, if you're trying to solve this Hamiltonian, if you need to, you can do it with brute force. So part A is solve it with brute force and see what you get. So if you are on the comprehensive exam trying to solve this thing and you don't have a moment of enlightenment, if you need to, brute force will work just fine. The brute force method is to write out this matrix in all possible states. This is 2 spin 1/2 particles. Each one can be spin up or spin down. That's an overall 4-dimensional space. And so if you have to, you can write out the complete Hamiltonian matrix and then just diagonalize it. So if you do that, this is what the matrix should look like. I recommend that you convert from sigma x and sigma y into the plus, minus, raising, and lowering operators. That makes it easy to get this form. If you do this, then you can answer the first part of that question: what are the energy levels? What are the degeneracies? Now, the intuition behind this is that if you have a dot product of 2 spins, that looks like the cross term from adding up angular momentum. And that's what should trigger the bell in your head that says, maybe I should use addition of angular momentum to solve this problem. So if you do that, you can show that if you take these operators, you can relate this to the total angular momentum j squared and jz squared plus a bunch of other crap. In general, that other crap could spoil the problem. Then it wouldn't be just a nice addition of angular momentum problem. But it just so happens that for the case of spin 1/2, all of that extra crap is just a constant. So when you put this together, You can find the energy eigenvalues of this Hamiltonian explicitly in terms of the spin quantum numbers of the total angular momentum. This should reproduce what you got in part A, and this should help you understand why the eigenvectors are what they are. And then the last part is coming from the second part of this question. Now a magnetic field is turned on. That magnetic field introduces a coupling to the total z component of angular momentum. So if you start off with these energy eigenvalues, now you add a new energy related to Jz, that will split the degeneracy in the problem. And then it asks you to sketch a plot of the energy as a function of the magnetic field. So my intention on this is to show you how to connect what we've been doing in class to the kind of things that you will need to be able to do for the comprehensive exam, and for this particular problem, to break it down and walk you through it step by step. Okay, I think that's everything that I needed to say as far as old business and new business. Are there any questions or comments before we start with physics for the day? Okay, let me stop the screen share and remember to pin my video this time. Also, by the way, I'm trying out some new chalk that's supposed to leave a lot less dust and make it easier for Dr. Paulone, who's in here after me. So if the chalk writing on the board is not visible, please let me know. Okay. So before we start with the hydrogen atom for this week, I wanted to revisit this operators that carry angular momentum. We started that at the end of last class, but we didn't get very far. So let's wrap up that discussion of operators carrying angular momentum. The point that I want to get across ultimately is that a vector operator, which we encounter many times in quantum mechanics, carries one unit of spin. And so this is really about relating the rotation of the operator to the rotation of the states. So we saw previously that the rotation operator on a vector is defined by u dagger of theta, one of the components of the vector operator, u of theta, is equal to the ordinary rotation matrix acting on the operator. So an operator transforms when you sandwich it between u and u dagger, and the effect of rotating this operator is you scramble its components by multiplying it by a regular 3x3 rotation matrix. This we found if you expand out what these operators are, writing this as e to the minus I over h bar j dot theta, whatever j may be for the problem at hand, this is equivalent to a set of commutation relations. Vi j sub j is I h bar sum over k epsilon I j k v k. So this is what it means. Either this statement or this one, they're completely equivalent. This is what it means for the operator to rotate like a vector. We want to express that information in spherical coordinates so that we can talk about total angular momentum and z component of angular momentum. So compare that to rotation of the angular momentum space. So if I have the state jz, and I hit it with the rotation operator u of theta, I can describe what this is doing by inserting a complete set of states. So let me insert j prime, jz prime. So this is a matrix which describes how the states, the angular momentum states, are rotated. One thing that we can immediately conclude is that this matrix element is 0 unless J is equal to J prime. By the way, I'm trying out these new colors. Supposedly these are brighter. For those of you online, can you see the red or no?
Not really.
Not really, okay. How about the orange that I used before? Is that better?
It's brighter than the red, but it doesn't look orange.
Okay, as long as it's visible and different from the white. Yeah, I was not hopeful about the colors here, unfortunately. Okay, so one thing we immediately know about this matrix is that this is going to have J equals J prime. That's because J is a scalar, right? This comes from the J squared operator. And this operator is invariant under rotation. So whatever quantum number J you have coming from the scalar operator can't change under rotation. So this object, if I write this as delta J, J prime, this is some matrix which is conventionally called D. It's a matrix between the Z components, JZ, JZ prime, and it knows about the value of J. So this is sum over J prime, J prime is now equal to J because I used the Kronecker delta, so it's just a sum over JZ prime. J, JZ prime, and then this matrix, I'm just going to keep it in this form. J, JZ prime, rotation operator, J, JZ. I'm not going to belabor this matrix or what its properties are. Suffice to say that it's an important matrix. It has a name. You can Google it and look it up if you'd like to know more. This is called the Wigner D matrix. It is the matrix element of the rotation operator in spherical harmonics or in the angular momentum states. You can calculate this thing explicitly if you have to, but it's messy. It looks very much like the calculation of the spherical harmonics. We're not going to need those details. The important thing that I want to set up is an analogy between this equation, where the rotation of the components is by this Wigner D matrix, this matrix element of rotations in angular momentum states, and this one describing how a vector rotates or how an operator rotates. So if this is what it looks like to rotate a vector in Cartesian coordinates, I wanted to write down an equation similar to this one where the rotation must look like this. This is how I define what my operator rotation is going to look like in spherical coordinates. So one thing is that my matrix, instead of being like this rotation matrix, Rij is going to be this matrix, the Wigner D matrix. The other thing is that notice that the rotation happens in the opposite order. This looks like the states, and then the matrix is to the right of it. This one looks like matrix, and then the operator is to the right of that. So it's in the opposite order. For that reason, I'm going to take this equation, and I'm going to take its transpose. I want to define this so it looks like that. That's why when I write this down in a second, instead of U dagger V U, I'm going to take the transpose of everything, and I'm going to have U V U dagger. And the matrix is going to be on the right of it. So all of that is by way of motivation. Let me leave this up here for one more moment. So this is my definition of an operator which rotates like it has angular momentum. I write U of theta OLM U dagger of theta equals sum over M prime OLM prime, and then this same matrix element, LM prime, rotation operator, LM. So this statement is supposed to be a synthesis or an analogy of the two ones that are then circled in orange. This one describing how an operator transforms. This one that says, I want my operator to transform like this if it's going to have its own well-defined angular momentum. So this is my definition. Again, there are words that can be associated with this. It's very awkward to try and read some of this stuff online. It gets very abstract mathematical very quickly. So these are referred to as spherical tensors, which basically means a matrix or an operator written in the basis of spherical harmonics and a result so it has its own angular momentum. Okay, so just like before, when I have this transformation of the operator, this is equivalent to a set of commutation relations. If I plug in for what the rotation operators are and I expand for an infinitesimal transformation, then what I obtain is the following. Ji OLM equals sum over m prime, OL m prime, Ln prime, Ji Ln. So you can sort of see if I plug in what the rotation operators are and I keep the linear terms that have J in it, this is what I'm going to get. And now I can calculate what this thing is for different choices of J. The simplest choice that I can make is, first let me consider Jz. Then I have Lm prime Jz Lm. Lm is an eigenstate of Jz. So this is immediately just mh bar delta m prime. So this tells me an operator which carries some angular momentum must commute with Jz, or sorry, the commutator with Jz should give you mh bar. That's what I'm trying to say. So Jz OLM equals mh bar OL. So that's one condition. This is what it means for the operator to carry m units of angular momentum along the z-axis. Its commutator with Jz, it's like an eigenvalue equation for the operator. So likewise, I can talk about Jx and Jy. Jx and Jy are messy when written in terms of this Lm basis. Instead, it's preferable to write them in terms of the raising and lowering operators, J plus minus. So I can write this whole equation basically taking I equals plus or I equals minus, since it's a linear equation and that's just a linear combination of x and y. When I have Lm prime J plus or minus Lm, then this raises or lowers that state correspondingly, and I get that funny square root eigenvalue. H bar square root L plus 1 minus M plus minus 1. And then I've either raised or lowered the state, so I get delta M plus or minus 1. So this gives me the other commutation relation, J plus minus OLM equals H bar square root L plus 1 minus M plus or minus 1. OL M plus or minus 1. So these commutation relations define what it means for an operator to have well-defined angular momentum. So you can apply this to any operator you want, but the only one that I really care about applying it to is the vector operator. So first, let me think about the z component. What part of the vector is going to have well-defined z component of angular momentum? Well, if I have something that commutes with rotations about the z-axis, then this commutator will be 0. So what I mean to say is that Vz is invariant under rotations about z. This follows directly from the rotation matrix that we wrote down to begin with. So this means u of, let's say, u of theta k Vz u dagger of theta k equals Vz. It's invariant. I think I should put my dagger on the other side, not that it matters. Yeah, so since this guy is invariant on the rotations about the z-axis, that means its commutator with jz is equal to 0. So that means that satisfies this equation, where m is equal to 0. Z, Bz equals 0. So that means I can identify Vz, the z component of any vector, as the part of that vector. I'm going to write it as Lm equals 0. I figured out that m is equal to 0 because it satisfies this formula with 0 component along the z-axis. The other thing that I know is that my vector has 3 components, Vx, Vy, Vz. And so that has to make up an angular momentum ladder with 3 states. That means it has to be L equals 1. 3 components, Vx, Vy, Vz. It must belong to a 3-state ladder of angular momentum. And that means it must have total angular momentum L equals 1, because there's only 3 independent components. So we found the first of these pieces, the trivial one. Vz is equal to, I'll call it V10. Total angular momentum is 1, z component is 0. What about the part of the angular momentum, or sorry, the part which raises or lowers the angular momentum? I'm going to use this. So if I plug in Vz, which I know has m equals 0, the commutator with j plus or minus will turn my V0 into whatever the corresponding V plus or minus 1 is. So using that equation, I have j plus or minus V10, and this guy is nothing more than Vz, is equal to h bar square root, let's see, L times L plus 1 is 2, since L is 1, minus m is equal to 0. So this is minus 0 times whatever the corresponding V1 plus or minus 1 combination is. So this is just square root of 2 h bar V1 plus or minus 1. So I can use this to figure out what the combination of the vector states which carries plus or minus 1 unit of angular momentum are. So from this, I have V1 plus or minus 1 equals 1 over square root of 2 h bar times the commutator j plus minus with Vz. This is 1 over square root of 2 h bar. J plus minus is jx plus minus ijy with Vz. And we already know what these commutation relations are. I wrote them down earlier. Those were, let me remind you, Eijj is I h bar sum over k epsilon ijk vk. This is from the rotation of the vector operator in Cartesian coordinates. And if I plug this in, what I get is v plus or minus 1 is minus plus 1 over root 2 vx plus minus I vy. So this is kind of the obvious answer. It's always been x plus or minus iy that was the relevant raising and lowering operator when it comes to angular momentum. There's a deep reason behind that that comes from writing these things in a spherical coordinate basis. So that spherical coordinate basis works no matter what operator you're talking about. So this means whatever operator I have, the part which is x plus iy will always deliver plus 1 unit of angular momentum. The part which is x minus iy will deliver minus 1 unit of angular momentum. The part which is vz will deliver 0 units of angular momentum. And all three together make up a spin 1 or 1 unit of angular momentum operator. Okay. Equivalently, you can solve this relation for vx and vy. So the reason that I'm discussing this is because this feature that your operator, your vector operator carries units of angular momentum is responsible for selection rules in Hamiltonians, especially when it comes to atomic transitions that we'll be talking about. So for example, one of the most important perturbations that goes into the hydrogen atom is the electric dipole moment. So this operator is some coefficient an external electric field dot the position operator. So this is the electric dipole moment. We heard the colloquium speaker last week talk a lot about the dipole approximation. The dipole approximation. I'm pretty sure this is what he's talking about. This is the dominant correction that leads to transitions or coupling to an external field. And it's driven by the vector position operator R. So that means when I have this Hamiltonian and I sandwich it between states Lm, L prime, M prime. That I can separate out what the different components of R are doing based on how much angular momentum they deliver. And that's going to tell me only certain numbers, or certain ones of these matrix elements can be non-zero. So when you plug in these components and you have something like, how did I write it over there? Lm. L prime, M prime, the Z component of the operator, Lm, we know that this is the Z component, or that 1, 0 projection of the vector operator. This is the position vector R, 1, 0. This carries 0 units of Lz. So this operator equals 0 unless Jz prime equals Jz. Because it delivers 0 units of Z component of angular momentum. L doesn't necessarily have to equal L prime. They can be different ladders that have the same value of Lz, but they do have to be compatible ladders. But this does put some constraint because they have to be compatible ladders. So you have to have something like L prime equals L plus 1 or L-1. You know that you've delivered 1 unit of angular momentum overall, so depending on how you add up the spins, this has to come from one of those ladders that you can get. Similarly, this is the real point that I wanted to get to here. L prime, M prime, if I have something like X, I can write both X and Y in terms of the +1 and -1 unit of angular momentum. So these kinds of matrix elements will be 0 unless M prime is equal to N plus or minus 1. Because I know that the X and the Y components are delivering 1 or -1 units of Z components of angular momentum. So these things show up when you start to calculate matrix elements in perturbation theory related to atomic transitions. I wanted to show you the reason for it. The reason is because the vector operator is delivering angular momentum. And conservation of angular momentum puts limits on which matrix elements can be non-zero. There's one other nice bonus to this about the discussion of rotational symmetry. It goes by the name of the Wigner-Eckardt theorem. I won't prove it, but it's easy to understand what it's telling us. So if you take a matrix element of an operator with well-defined angular momentum between two different angular momentum states, this problem looks like an addition of angular momentum problem. It looks like you started off with this much angular momentum, you added this much to it, and you tried to project it onto this state. So this has something in common with calculating Clebsch-Gordon coefficients. So this is some constant or some coefficient, J prime L J times J prime JZ LM J JZ. So the physics is this looks like addition of angular momentum. Just like we talked about with states. It looks like you took something that started off with J and JZ, added to it a new source of angular momentum with values L and M, and you're asking when can this be equal to total angular momentum J prime JZ prime? And that's what's reflected here on the right. You expect that this should have something to do with Clebsch-Gordon coefficients because that's how you do this addition of angular momentum. And indeed it does. It's proportional to the Clebsch-Gordon coefficients. This carries all of the directional information. This is the only thing that can depend on JZ and sorry, I dropped the prime here, JZ prime. All of the Z information about the orientation of the vector is contained within the Clebsch-Gordon coefficient. What's left over, this one, doesn't care about the direction, only the magnitude of angular momentum. Independent of direction. So that means it doesn't depend on JZ, doesn't depend on M, doesn't depend on JZ prime, only depends on the total angular momentum in question. So this is called the reduced matrix element. The point is, it is independent of direction. It has rotational symmetry. The information about the directions you can get when you add up angular momentum is completely contained in those Clebsch-Gordon coefficients. And whatever's left over, everything that's unique about this operator, whatever it is, cannot depend on the direction. It can only depend on the magnitude. So this is a big advantage because it means you don't have to calculate all of the components. You can calculate one of them, say of the vector operator, and then you can immediately figure out what the other two are by relating them to the Clebsch-Gordon coefficients. So for example, how is this helpful? You can calculate something simple like the matrix element of JZ. J prime, JZ prime, VZ, J, JZ. This guy is equal to some reduced matrix element that doesn't care about JZ, J prime 1J, times the Clebsch-Gordon coefficient, J prime, JZ prime 1, 0, J, JZ. So this comes from identifying this as an operator that has L equals 1, N equals 0. So this gives you some coefficient that knows that you added L equals 1, and all of the direction information about M is contained in that Clebsch-Gordon coefficient. You can just write it down, you can look it up in a table. Once you know this, and you know what that Clebsch-Gordon coefficient is, you immediately know how to calculate the other matrix elements. Because then, once I know that, I have J prime, JZ prime, Vx, J, JZ, and Vx we said was minus plus 1 over root 2, J prime, JZ prime, V1, it was negative 1, and then I subtract it, plus 1, J, JZ. Right, once you know the value of that coefficient, and I ask you for Vx, you can replace Vx in terms of the plus minus 1 components. And those are just the same coefficient C that you calculated the first time, and the only difference between them is the Clebsch-Gordon coefficients that go along with it. Okay, so I apologize if all of this is a bit esoteric, but this is something that's going to come back to us later, and I wanted to preview it now. So the point is, the unique information about what this operator is doing is completely contained in that coefficient. All the directional information comes in the form of a Clebsch-Gordon coefficient that you can look up in a table. So if you can calculate this thing and figure out what that coefficient is, if you want to calculate any other component like Vx, you plug in that same answer you got the first time, times a different combination of Clebsch-Gordon coefficients that you can look up in a table. So you do not have to repeat the calculation for Vx, Vy, and Vz. You can calculate one of them and use rotational symmetry to immediately figure out the others. And that comes in the form of the Clebsch-Gordon coefficients. Okay. That was the last thing that I had wanted to say about rotational symmetry. And now moving on to the hydrogen atom for this week. Any questions before we change topics? All right, so our approach to the hydrogen atom this week is going to be very similar to our approach to the harmonic oscillator last semester. First, we will solve the problem with brute force by writing down the differential equation for the Schrodinger equation and then just solving it. That will involve techniques about differential equations, finding the asymptotic solutions, pulling out that behavior, trying a series ansatz, whole song and dance that we did for the harmonic oscillator. For the harmonic oscillator, that led to, well, the answer is called a Hermite polynomial. This time it's going to lead to, well, the answer is called a Laguerre polynomial. What you learn from that, I don't really know, but that's the standard way of doing it. It's the brute force approach, and it will give you the correct answer. So one is brute force differential equations series ansatz. And then the second approach, which is less common, is purely algebraic. We will identify the symmetries of the Hamiltonian, and we will exploit that symmetry group to determine what the answer is. So this is algebraically by symmetry. We will take advantage of an extra conserved quantity that exists for the hydrogen atom or for gravity for any 1 over r potential. There's an extra conserved quantity called the Runge-Lenz vector. Sometimes called the Laplace Runge-Lenz vector. This may or may not be something that you've already seen in classical mechanics or one of your other classes. Can I get some indication? Have you guys encountered this before in your other classes here? No?
No.
Okay, then we will go through that slowly. So ultimately, this lets us write down the properties of the hydrogen atom as rotation symmetry, not in 3 dimensions, but in 4 dimensions. And this extra vector acts like an extra angular momentum that is giving you an extra source of rotation in 4 dimensions. So we will again solve algebraically, and the presence of this extra conserved quantity will explain certain degeneracies of the hydrogen spectrum that were completely not obvious this way. So let's start off with the standard method today. We may not get all the way through it, but we'll get most of the way there. And then on Wednesday, we will wrap this up and we will set up the algebraic calculation. But this is very similar to what we did for the harmonic oscillator, where first we did it by brute force differential equations, and then we did it in terms of A and A dagger. And A and A dagger wind up being the more powerful way to approach the problem. And I think it's very similar to the hydrogen atom. Okay, so for the hydrogen atom, the potential that we have in 3 dimensions is the Coulomb potential. You have V of R is minus E squared over R. So this is the potential where you have a positive charge with charge plus E interacting with an electron that has negative charge minus E at a distance R. No thought necessary. We just have to write down the Schrodinger equation and then hit it with Mathematica and see what I get. So the Schrodinger equation in 3 dimensions is minus h bar squared over 2 times the mass. I will again call the mass mu, so as not to confuse it with the angular momentum quantum number m. Minus e squared over r. Helps if I write the Laplacian. Sine equals E psi. So this is the 3-dimensional time-independent Schrodinger equation. We saw last semester that for any problem that has rotational symmetry, where the potential depends on R but not the angles, that you can separate out the angular behavior into spherical harmonics. This translates into an effective 1-dimensional equation, minus h bar squared over 2 mu d squared dr squared plus h bar squared L plus 1 over 2 mass times r squared UL of R equals E UL of R. This is the effective 1D time-independent Schrodinger equation. In making this translation, we generate an effective contribution to the potential. This is called the centrifugal barrier. This is effectively a repulsive potential energy that comes from the rotational kinetic energy the object has. If you have angular momentum, it's very hard for you to slow down and sit at r equals 0. This acts like a repulsion proportional to 1 over r squared. When we solve this thing, notice that the 1 over r squared here is more powerful than the 1 over r for the potential when you start to get close to the origin. This is going to help determine what dominates the asymptotics of this differential equation. So this quantity U is what I call the radial probability amplitude. It comes from decomposing the Schrodinger equation in the wave function psi Lm of r, theta, and phi into some radial function Rl of r times the spherical harmonics Ylm of theta and phi, and then shifting this radial function by a factor of r. So this is defined to be 1 over r ul of r, Ylm of theta and phi, so that ul of r is r times rl of r. And that's what gives you ul of r squared is r squared rl of r squared. And this r squared is a way of absorbing in the measure in spherical coordinates, so that you have integral dr from 0 to infinity of this guy is equal to integral dr 0 to infinity, which is 1 over 4 pi, probably an overall factor of 4 pi. Yeah. Integral d3r rl of r squared. So just to remind you, this has a physical interpretation, that this is like the wave function, the one-dimensional wave function as a function of r, only the reason that it has this extra factor here is because you are absorbing the r squared from the three-dimensional volume element in spherical coordinates. All of that is just to remind you of the physics. It has nothing to do with the mathematics that we can just blindly perceive it. What am I doing on time? 20 minutes. Okay. So now it's just a differential equations exercise. We would like to solve this differential equation. So let's introduce dimensionless variables and shift the equation around. So if I rearrange the equation, I can write it as d squared dr squared plus 2 mu over h bar squared e plus e squared over r minus h bar squared L of r plus 1 over 2 mu r squared. So I gather all the terms on one side, so I've got 0 on the other side. Now let's examine the dimensions. This derivative has units of 1 over length squared. This coefficient, 2 mu energy over h bar squared, also has units of 1 over length squared because it gets added to that derivative. So my natural length scale if I say 1 over a squared is equal to 2 mu e over h bar squared, then this is equivalent to saying a is square root h bar squared over 2 mu. And I'm going to put absolute value of e here. Put absolute value of e here as well. Because we can consider both the positive energy solutions, which are free electrons that are not trapped in the potential. They have the ability to escape to infinity because they have positive total energy. And we can consider the bound states where the energy is negative and then the electron is trapped. Okay, if I pull out this overall factor of A, then I can define a dimensionless length I'll call it R tilde, which is R divided by A. If I rewrite the differential equation in terms of this dimensionless length, then I get d squared dr tilde squared plus the sign of the energy could be positive or negative. So we will shortly specify that we're only really interested in solving the bound states, but I'm going to hang on to this for just a moment longer so that we can talk about the free particles as well. So just to remind you, this is a number which is +1 if the energy is greater than 0. It's -1 if the energy is less than 0. This thing formally is equal to energy divided by its absolute value. So it came because I had energy in the equation and I pulled out the absolute value of it. Okay, this gives me one other unit that I should introduce. This is dimensionless. The whole thing is dimensionless, so this is some dimensionless quantity up there. So I will call, actually not the electron charge. Let me call this lambda. I plug in that A, this is equal to 2 mu over h bar squared, absolute value of the energy. So just choosing convenient symbols to make the math a little bit more compact. And what I'm left with is d squared dr twiddle squared plus sine of the energy plus lambda e squared over r minus L plus 1 over r squared UL of r equals 0. Make sure my signs are right. Plus, okay. We haven't done anything to the differential equation yet. We've just introduced some scaling variables. Now let's examine the asymptotics of this solution. So first, let's take a look at the behavior near r equals 0. So this is the dimensionless variable r tilde much less than 1. So when r tilde is small, these two terms start blowing up. I've got 1 over r and 1 over r squared. Which one wins?
It depends on where you are, right? I mean, generally r squared would win if r is big.
Well, we're considering here r is small. And it's 1 over r and 1 over r squared. So I think your answer is still the same, except we're going in the opposite limit. Right? 1 over r blows up to infinity when r goes to 0. 1 over r squared also blows up to infinity, but it goes there faster. So if I take this differential equation in the limit when r is going to 0, this constant, irrelevant. This is going to infinity, but not fast enough. The thing that dominates is the centrifugal barrier. As long as L is not equal to 0. If you have any angular momentum at all, that centrifugal barrier dominates the behavior at r equals 0. If L is not equal to 0, the centrifugal barrier dominates. So in that case, for r twiddle much less than 1, my differential equation simplifies, and it looks like d squared dr twiddle squared minus l plus 1 over r twiddle squared ul of r equals 0. So this is equivalent to d squared ul dr twiddle squared equals l plus 1 over r twiddle squared ul of r twiddle. So this kind of suggests that some polynomial or power law behavior will work. Because here I have two derivatives that's going to subtract 2 from my power. Here I take whatever I have and I divide the power by 2. That will also take my exponent down by 2. So this suggests a power law type solution. Check and see that if our guess is ul of r goes like r to some power alpha, that this can solve the differential equation and figure out what value of alpha we get. So if I plug this in, when I take one derivative, I get alpha, r to the alpha minus 1. Take a second derivative, I get alpha minus 1, r to the alpha minus 2. On the right-hand side, I have L plus 1, and then I have r to the alpha, and I subtract 2 because I divide by 2 powers. Lo and behold, the guess works. Loosely speaking, I say I can cancel those factors, and I ask what values of alpha will work. So clearly, if alpha equals L plus 1, then this is L plus 1 times L. That's one solution. Or alpha equals negative L. Then I have negative L over L minus sign L plus 1. So this would correspond to ul of r goes like r to the L plus 1. This one would have ul of r goes like 1 over r to the L. This one is perfectly well behaved when r goes to 0. This one has the wave function blowing up when r goes to 0. This one is not mathematically possible. This violates normalization conventions. So this is impossible to normalize, because then this means that my radial wave function r, L of r, will go like 1 over r to the L plus 1. And if I take this and I try to integrate it, let's say integral, it's probably easiest to write it in this way. Integral 0 to infinity dr ul of r squared. This is going to go like 0 to infinity dr 1 over r to the 2l. Yeah, 1 over r to the 2l. And this is going to give me something which is infinite. When r goes to 0, this blows up so badly that the wave function can never be normalized to 1. So this solution, although it exists as a mathematical solution to the differential equation, is unphysical. This is not a valid candidate. So the solution when r goes to 0 must be polynomial r to the L plus 1. So that's the first piece of information. That's the behavior as r goes to 0. We've got 10 more minutes. Let me just comment that here we did this assuming that L was non-zero. The story changes a little bit in the analysis when L is equal to 0, but the answer does not. This answer still works even for L equals 0. I guess I should have erased the full differential equation there. writing it back. All right, so we already figured out the asymptotics when R goes to 0. Now let's ask about R goes to infinity. So this is the limit when the dimensionless variable R tilde is much larger than 1. Now when R goes to infinity, I have some constant, 1 over R goes to 0, 1 over R squared goes to 0 even faster. So I'm going to throw this out, and I'm going to throw this out, and I'm just going to keep the trivial part. And this gives me d squared u dr squared equals minus sine of the energy UL of R. So easiest just to write this out in terms of separately for positive and negative energies. D squared u dr squared equals negative UL of R if energy is positive, d squared u dr squared equals positive u if the energy is negative. So this equation is totally separable. This has the trivial solutions. This one is the plane wave. This one is the decaying exponential. So for energy greater than 0, we get free particles asymptotically. UL of R goes like e to the plus or minus I R tilde. We already wrote it in dimensionless form, so the wavelength is already buried in there. And for energy less than 0, we get decaying exponential. Okay, this is all that I wanted to say about the free particle. If the energy is positive, then you do in fact see that yes, when the electron is very far away from the proton, it just travels like a free particle, a plane wave. If the electron is bound to the proton, then you get something which is a decaying exponential, the same way we already saw in one dimension when your kinetic energy was less than the potential energy, and so the particle was like decaying inside a barrier. So something like this. Free particle, decaying exponential inside a barrier. Okay. I don't think we're going to have time to solve the series on sides, but we can at least set it up. All right, so now that we know the asymptotics, let's remove them and just keep the polynomial parts. So explicitly include the known asymptotics. So we have UL of R twiddle is e to the minus R twiddle from the large distance asymptotics. Here now I'm considering only negative energy solutions from here on out, only bound states. Times some other function VL of R. So this is the large R asymptotics. And this is some polynomial. And I know not just any polynomial, I know what term is the smallest term in that polynomial. It can't be 1 plus something, because then when R goes to 0, it wouldn't match on to R to the L plus 1. So it must be some polynomial starting at r twiddle to the L plus 1. Could have higher order terms that are less important when r goes to 0, but this is the most important behavior when r goes to 0. So if I take now this form and I plug it back into this equation, now I'm going to take the energy to be negative, so this is now explicitly minus 1 lambda e squared over r minus L plus 1 over r squared. And now I'm plugging in e to the minus r tilde VL of r tilde equals 0. So these are just constants. They multiply both functions. The only thing I have to work out a little bit is the derivative. Remember that you have product rules. So every time I take the derivative, I have to hit both the exponential and v. So when I do this, I get d squared, dr squared minus 1, acting on that combination, e to the minus r VL of r. If you open up the parentheses, you get e to the minus r VL double prime minus 2 VL prime. Basically, pulling out that exponential asymptotics lets us kill the 1. And then you get the second derivative term and the first derivative term. So using this and removing those asymptotics now gives us a differential equation just in the polynomial parts. So we've reduced it down to a differential equation for some polynomial. The answer ultimately are called the Laguerre polynomials. And just like for the harmonic oscillator, we will construct them by series ansatz. The last thing that I'm going to write down is the starting point. We will say VL of R is some series. It has to start with R to the L plus 1 in order to match onto the short distance asymptotics. And it could have any higher powers than that. J equals 0 to infinity, unknown coefficient C sub j, R twiddle to the j. So this overall is sum j equals 0 to infinity, C sub j, R twiddle to the power L plus j plus 1. So we will stop here, but the next step clearly is to take that series ansatz and plug it back in here and try and figure out what the coefficients are. Once you figure out what the coefficients are, you have solved the differential equation and you have the full answer. Okay, any questions? All right, if not, thank you guys very much, and I will see you on Wednesday where we will wrap this up.